So if you were to take a control dial, right, and just nudge it by like 1 millimeter, every single star in the sky would instantly rip itself apart.
Yep.
Instantly.
It's insane. Reality as we know it is just, it's balanced on a knife's edge so extraordinarily thin that it really defies all conventional logic. So welcome to this edition of Audio Notebook. Today we are staring directly at the absolute foundation of our existence.
We really are.
Because when you look up at the night sky, our universe appears incomprehensibly vast. It's ancient, sweeping, and seemingly indestructible. But its ability to harbor any complex structure whatsoever, whether we are talking about a supermassive star burning in the deep void, or just the intricate biological machinery of us sitting here having this conversation, it all rests on a terrifyingly precise balancing act.
Right, which is the absolute definition of cosmic fine-tuning. And to truly understand the stakes we are dealing with here, you have to realize what physically happens if we barely touch these fundamental dials.
We aren't just talking about a slightly altered universe where humans never evolved or where the sky is a different color. We are talking about mathematical thresholds where the universe either violently collapses immediately back into a microscopic singularity or rips itself apart into a freezing, hyper-dilute void where no two particles ever touch.
Or it just stays an infinite soup, right?
Exactly. It just remains a featureless soup of dilute hydrogen gas for all eternity. So, no stars, no planets, no carbon, no chemistry, just nothing.
That sheer scale of fragility is it's mind-blowing. And that's what we're going to explore today. Our mission for this audio notebook is to take you on an exhaustive step-by-step journey. We're zooming in to the absolute smallest subatomic particles, and then we're going to pan out to the very edge of the cosmos.
To try and understand why reality is built this way.
Exactly, leaving absolutely no detail unturned.
Which means we need to start at the very bottom.
Yeah.
The first principles.
Okay, lay it on me.
Well, before we can even begin to talk about the macroscopic universe like galaxies and black holes, we have to look at the foundational mathematical dials that control them. In physics, we have what are known as free parameters.
So these are the numbers that just exist, like the ones we can't explain.
Precisely. In the standard model of particle physics and in the lambda CDM model of cosmology, there are constants that we literally have to insert by hand. We can't derive them from some elegant mathematical theory. They just are.
Wow.
We measure them experimentally, in a lab or through a telescope, and we just plug them into our equations to make the math actually work.
It's like walking deep into the woods, finding a massive humming machine, and you don't know who built it, but you look at the control panel, and someone has manually set the dials to very specific, seemingly arbitrary numbers.
That's a great way to look at it.
And the very first dial on this cosmic control board is the strong nuclear force. So let's break this down, because if you're listening to this right now, just look at the device in your hand or the table in front of you. The only reason the atoms in that object are holding together is because of this specific force, right?
That's exactly right. The strong nuclear force is the fundamental glue of reality. To understand why it's necessary, you have to remember that the nucleus of an atom is packed with protons, which all have a positive electromagnetic charge.
And positive charges violently repel one another.
Right. Left to their own devices, the protons in an atom's nucleus would instantly blast apart. So the strong nuclear force is the incredibly powerful, very short-range force that overpowers that electromagnetic repulsion and binds the protons and neutrons together.
It forces them to share a space they desperately want to escape.
Exactly. And in the context of the wider cosmos, this force governs nuclear cohesion. And vitally, it controls the rate of nuclear fusion within stellar cores. We measure its practical efficiency with a parameter denoted by the Greek letter epsilon. And currently, the dial for epsilon is set to exactly 0.007.
0.007. So roughly 0.7% of the mass of protons and neutrons is converted into energy when they fuse.
Yes.
What happens if we mess with this dial? Walk me through the actual physical consequences if we turn it down just a tiny fraction. Say it drops from 0.0007 to 0.006.
Well, at 0.006, the strong force is simply too weak to overcome the electromagnetic repulsion. It cannot bind protons and neutrons together effectively enough to build anything complex. The universe becomes completely unable to synthesize any element heavier than hydrogen.
Meaning, wait, no carbon, no oxygen?
None. Carbon, oxygen, nitrogen are the fundamental building blocks of all complex chemistry. They become physically impossible to forge. They're wiped off the periodic table. You are left with a cosmos that has absolutely zero molecular diversity. No water, no rocky planets. Just an endless expanse of simple hydrogen gas floating in the dark.
Okay, so dropping the dial is an apocalyptic scenario for chemistry. But what if we turn it up? Because, human intuition says stronger is better. What if we make the strong force stronger? Let's say epsilon goes up to 0.0008.
It is equally catastrophic, but in the exact opposite direction.
Really?
Yeah. If epsilon goes above 0.007, the strong force becomes hyper-efficient. It's too good at its job. Because it's so strong, hydrogen fusion becomes incredibly easy. What happens physically is that during the initial heat of the Big Bang, all of the primordial hydrogen is instantly burned up and fused into heavier elements within the first few minutes of existence.
Wait, all of the universe's hydrogen just goes up in smoke?
Almost all of it. And that is a fatal problem, because hydrogen is the essential slow-burning fuel for stars. Stars like our sun rely on hydrogen to burn steadily over billions of years, which creates a massive, stable window of time for planets to form and life to incubate.
Oh, I see.
Without that leftover hydrogen, you get a cosmic flash in the pan. The stars burn through their heavy fuel with terrifying speed, go supernova almost immediately, and you are left with a dark, dead universe, choked with heavy metals and zero light.
So it's 0.007 or bust. That's incredible. But as we move down the control board, we hit a dial that governs a massive conflict between two forces we interact with every single day: gravity and electromagnetism. In physics circles, this is famously known as the hierarchy problem, right?
Yes. The hierarchy problem is arguably one of the most glaring and frustrating mysteries in modern physics. It refers to the vast, almost comical disparity between the strength of gravity and the strength of electromagnetism.
How big is the gap?
To put the actual number on it, electromagnetism is an astonishing 10 to the 36th power times stronger than gravity.
Hold on, I want to make sure we really grasp the sheer absurdity of that number. 10 to the 36th power. That is a 1 with 36 zeros after it. Let me put it this way for you listening. I can reach down and pick up a paperclip with a tiny, cheap refrigerator magnet. In that moment, that tiny little magnet in my hand is successfully overpowering the gravitational pull of the entire planet Earth.
Yes.
The entire mass of the Earth is pulling down on that paperclip, and my fridge magnet is winning. That is how pathetic gravity is compared to electromagnetism.
That is the perfect way to illustrate it. Gravity is astronomically weak, but the fine-tuning puzzle asks, what happens if we try to fix that disparity? What if we turn gravity's dial up closer in magnitude to the electromagnetic force?
Again, my intuition says things would just hold together better. We'd have sturdier galaxies, tighter solar systems.
They would stick together far too aggressively. If gravity were significantly stronger, matter would clump with terrifying speed and intensity in the early universe. The stars that form would be hyperdense. And because they are so massive and tightly packed, the gravitational pressure in their cores would be immense. That pressure accelerates nuclear fusion exponentially. So instead of a star like our sun burning steadily for 10 billion years, these hyperdense stars would burn through their entire nuclear fuel supply in millennia.
So a star ignites, burns furiously, and dies out before chemistry even has a chance to figure out single-celled organisms.
Precisely. Biological evolution is a process that requires deep time. A universe with stronger gravity fundamentally denies biology the clock it needs to function.
Okay, so let's spin the dial the other way. If gravity is already weak, making it even weaker seems like it would just let everything dissolve.
It does. If gravity were any weaker, electromagnetic repulsion would completely dominate the cosmos. The universe's expansion would stretch matter out, and gravity wouldn't have the strength to pull clouds of gas together.
Everything just drifts apart?
Right, particles would literally refuse to stick together in large quantities. Galaxies would fail to form. Gas clouds wouldn't collapse to ignite stars. Planets wouldn't coalesce. The universe would just be an ever-expanding, freezing cloud of mutually repelling dust.
So the strong force has to be exactly 0.007. Gravity has to be exactly 1 trillionth the strength of electromagnetism. But as we keep looking at this control panel, it gets even more granular, doesn't it? It's not just the forces, it's the actual mass of the particles themselves.
Right, we have to look at the proton-to-electron mass ratio. In physics, this is represented by the Greek letter mu, and its value is approximately 1836.15, meaning a proton is roughly 1,836 times heavier than an electron. We also have to look at the mass difference between neutrons and protons, which is incredibly tiny, about 1.293 mega-electron volts.
I want to paint a visual picture here, because for decades, textbooks taught us to picture atoms like planetary systems, a big sun in the middle, and electrons orbiting like tiny planets. But quantum mechanics tells us that's not really how it works. Electrons exist in probability clouds.
Yes, exactly.
So instead of a planetary orbit, think of it like the exact tension on a guitar string. The mass ratio of 1836:1 is the exact tension required to tune that string so it can play the specific chord of complex chemistry. It dictates the size and shape of electron orbitals, which determines how atoms bond together to make molecules.
That's a great analogy.
If you change that mass ratio, you tighten or loosen the string. The orbitals warp, chemical bonding becomes intrinsically unstable, and the music of biology just stops.
That is a much more accurate way to visualize it. The physical geometry of chemistry is completely reliant on that mass ratio. But you mentioned the neutron-proton mass difference, and that is where the physics become truly precarious.
Because neutrons are slightly heavier than protons, right?
And because of that tiny excess mass, free neutrons are inherently unstable. If you isolate a neutron and just leave it sitting in a vacuum, it will decay. It turns into a proton, an electron, and an antineutrino with a half-life of roughly 614 seconds.
So just over 10 minutes.
Right. But here's the critical threshold. What if the mass difference between the neutron and the proton were smaller than the mass of an electron? Meaning, if the difference was roughly 1/3 of what we actually observe today, the entire energy dynamic of the universe reverses.
Wait, I need to make sure I understand this. If that tiny mass difference shrinks, the math flips, and protons suddenly become the unstable ones. Do protons just start capturing their own electrons, turning into neutrons, and atoms fundamentally cease to exist?
That is exactly what happens. It triggers a runaway electron capture event across the entire cosmos. Protons would routinely capture the electrons in their orbitals. Every single proton in the universe would essentially eat its own electron and turn into a neutron.
Wow.
The universe would instantly transform into a sea of neutral particles.
Yeah.
No protons means no atomic nuclei. No atomic nuclei means no atoms. No atoms means no reality as we know it.
That is genuinely apocalyptic. We've gone from adjusting a guitar string to the universe literally deleting its own structural integrity because a subatomic particle was a tiny fraction of a percent too light.
And if that level of precision feels precarious, we have only been talking about the infinitesimally small building blocks of matter. If we scale up from the quantum realm to the macroscopic universe, we encounter an even bigger mathematical crisis.
So we've looked at the microscopic pieces, the atoms, but what happens when we zoom out and look at the empty space between them? The void itself. Because this is where we find the most embarrassing mathematical discrepancy in the history of science. We're talking about the vacuum catastrophe.
The vacuum catastrophe centers around the cosmological constant, which is often represented by the Greek letter lambda. This is fundamentally tied to dark energy. Dark energy was discovered observationally in 1998, and it is the mysterious, repulsive force that is accelerating the expansion of our universe.
Okay, so the first thing we need to wrap our heads around is that emptiness isn't actually empty.
Far from it. According to quantum field theory, or QFT, the vacuum of space is a highly dynamic, roiling arena. It is literally teeming with fluctuating zero-point energy. Even if you remove every single particle, every photon, every atom from a box, the quantum fields inside that box are still vibrating.
Like particles popping in and out.
Yes, particles and antiparticles are constantly popping into and out of existence up to the Planck scale cutoff.
It's like an ocean that looks calm from a distance, but when you look closely, the surface is constantly boiling.
Exactly. Now, when theoretical physicists use QFT to calculate how much energy should be in this boiling vacuum, the resulting theoretical value they get is astronomically massive. It's on the order of 10 to the 18th power gigaelectron volts.
But physics is about observation. When we actually point our telescopes at the sky, look at how fast galaxies are moving away from each other and measure how much energy is actually pushing the universe apart. What do we find?
We find that the actual physical density of the vacuum energy is roughly 10 to the negative third power electron volts.
I want to pause here and break down that discrepancy, because this isn't just a minor rounding error. It is universally known among physicists as the worst theoretical prediction in the history of science.
It really is.
The difference between what quantum mechanics predicts empty space should weigh and what it actually weighs is 120 orders of magnitude.
10 to the power of 120.
That is a 1 with 120 zeros. To really give you a sense of scale for how wrong that math is, there are only about 10 to the 80th atoms in the entire observable universe. So the error in this equation is a trillion times larger than the total number of atoms in existence.
It is a devastating mismatch, and here is where the fine-tuning aspect rears its head. The vacuum energy must be canceled out by some unknown mechanism to a precision of 1 part in 10 to the 120th power. It's a razor's edge. If this value were even slightly more negative than it is, the attractive force would overpower the expansion, and the universe would have instantly collapsed back on itself in a big crunch. If it were slightly more positive, the repulsive force would be so strong that the universe would have flown apart so rapidly that galaxies, stars, and planets could never have coalesced.
It is functionally identical to having a bank account where $1 quadrillion is accidentally deposited, and simultaneously $1 quadrillion is withdrawn by a completely different system, and the remaining balance is exactly 1 penny, purely by coincidence.
That's exactly what it looks like mathematically.
It defies all logic, but I know theoretical physicists haven't just accepted this. There have been some massive theoretical resolutions proposed very recently, right around the 2024 to 2026 timeframe, to try and fix this math.
Yes. The profound nature of this problem has led to some highly innovative frameworks that attempt to explain the vacuum energy without relying on arbitrary, miraculous fine-tuning. One of the most prominent is pre-geometric gravity, or PGG, a theoretical framework published in 2026.
Pre-geometric gravity. What does that mean?
It suggests that space-time itself isn't a fundamental pre-existing backdrop that particles just move around in. Rather, space-time emerges from the breaking of a fundamental gauge symmetry.
Okay, hold on. You just threw gauge symmetry breaking at me. I need a visual for that. Are we talking about a physical force field shattering?
Think of water freezing into ice. When water is a liquid, it has high symmetry. It looks the same in every direction, and the molecules move freely. But as it cools and freezes, that continuous symmetry breaks. It snaps into a rigid, specific structure, a crystal lattice.
Oh, I see.
PGG posits something very similar for the fabric of reality. In the extreme heat of the early universe, space-time didn't have a fixed geometry. But as it cooled, the symmetry broke, and space-time basically crystallized into the structure geometry we observe today.
Okay, I can visualize that, the universe freezing into a structure. But how does that fix the 120 orders of magnitude error?
In this model, there is a complex topological element called the Gauss-Bonnet coupling.
Gauss-Bonnet coupling, again, I'm going to need you to unpack that. Topology usually deals with shapes, right? Like donuts and coffee mugs.
Yes. Topology is the mathematical study of properties that are preserved through deformation, twisting, and stretching. The Gauss-Bonnet coupling acts as a gravitational theta angle. Imagine a topological feature, like a twisted Mobius strip. You can bend it and stretch it, but you can't undo the twist without cutting it.
Right.
The mathematics of PGG suggests that the universe has a topological twist that scales precisely as the de Sitter entropy, which happens to be proportional to that massive 10 to the 120th figure.
So because of the specific way space-time folded and crystallized, the vacuum energy is physically restricted.
Precisely. This underlying topological dynamic forces the cosmological constant into discrete quantized sectors.
Yeah.
The vacuum energy isn't allowed to just be any random massive number that QFT predicts.
Yeah.
The symmetry breaking dynamics naturally select the small vacuum energy we observe. And what's brilliant about this theory is that it proposes a massive potential barrier that seals it off.
Like the twist in the Mobius strip resisting being flattened.
Exactly. It prevents the vacuum energy from quantum tunneling into other higher energy states. It's mathematically locked in.
That is incredibly elegant. It takes away the coincidence and replaces it with geometric necessity. But there was another major breakthrough around the same time, right? The information theoretic decoherence resolution in 2026. And this one traced the massive error not to topology, but back to a fundamental counting mistake in the math.
Yes. This framework is completely different. It argues that the 10 to the 120th discrepancy stems from incorrect degree of freedom counting that violates holographic bounds. The physicists tackled it using Shannon entropy of dimension-weighted causal sectors, combined with cosmic scale decoherence irreversibility.
Whoa, okay, let's pump the brakes. When I hear Shannon entropy, I think of information theory. I think of file compression on my computer, like zipping a folder to send an email. Are you saying the universe is zipping files to save space? How does a computer science concept dictate the physical expansion of galaxies?
It's a fascinating connection. In computer science, Shannon entropy measures the amount of uncertainty, or the true information content, in a data source. It asks, how compressible is this file? How much redundant information is there that we can safely ignore?
Oh.
In the context of the universe, this 2026 resolution treats the cosmos fundamentally as an information processing system.
So space itself holds data.
Yes. The traditional QFT calculation, the one that got the answer wrong by 120 orders of magnitude, essentially counted every single possible quantum fluctuation at every microscopic point in 3D space as a completely independent, unique piece of information. It added them all up. But we now know about the holographic principle.
Right, the idea that the universe has a strict data limit.
Exactly. The holographic principle dictates that the maximum amount of information a volume of space can hold is bounded by its 2D surface area, not its 3D volume.
It's like trying to fit a terabyte of unique data onto a gigabyte flash drive. The flash drive physically cannot hold it, so the old QFT calculation was counting data points that the universe physically cannot store.
You nailed it. QFT was counting redundant information. By applying Shannon entropy to classify these causal sectors, properly filtering out the redundant data and factoring in how quantum states decohere, these scientists derived a parameter-free dark energy density. They didn't have to put any arbitrary dials in by hand. They calculated the density parameter, omega lambda, purely from information theory to be 0.6841.
And how closely does that purely theoretical number match our actual observations of the universe?
It matches the European Space Agency's Planck satellite data to within 0.09%.
That is staggering. A mathematical derivation based on how the universe processes data, matching the physical expansion of the cosmos to less than 0.1%. It completely bypasses the flawed QFT prediction.
It's a massive leap forward.
Yeah.
But it also leads us into a deeper philosophical and physical argument.
Right. Because if tweaking just one dial destroys the universe, what happens if we tweak two at the same time? Are physicists accidentally rigging this game by looking at these forces in a vacuum? We say, if you change gravity, everything breaks. But what if you change gravity and electromagnetism proportionally at the same time? Are we artificially holding the other dials constant to make the fine-tuning look worse than it really is?
That is the crux of a fierce, highly technical argument in astrophysics, primarily championed by Luke Barnes on one side and Fred Adams on the other. It's all about mapping the full parameter space.
Let's start with Barnes. He's firmly in the camp that the fine-tuning is absolutely real, right?
Very firmly. Luke Barnes argues against the one-at-a-time critique you just mentioned. He points to extensive multidimensional explorations of the parameter space, specifically studies by physicists like Stephen Barr, Yashar Khan, and Max Tegmark. These studies don't just spin one dial, they vary multiple constants concurrently. They put all the forces into a supercomputer and scramble them together.
And what happens when you do that? Doesn't that open up a lot more combinations that work?
Not according to Barnes. He notes that fundamental parameters are physically bounded by the Planck scale. They don't have an infinite range. You can't just spin the dial forever. And when he calculates the complete multidimensional parameter space concurrently, he finds that the life-permitting regions are still vanishingly small. He calculates a staggering 1 in 10 to the 136th power chance of landing on a life-permitting configuration by pure naturalistic chance.
1 in 10 to the 136. So Barnes says the universe is basically a cosmic lottery winner, even when you let all the numbers shift at once. But Fred Adams pushes back hard on this conclusion.
He does. Fred Adams ran his own semi-analytical models. He varied gravity, the fine structure constant, and composite nuclear reaction rates all simultaneously. He essentially built a computational universe and let the physics play out across billions of different simulated permutations.
And what did his simulations find?
He found that approximately 25% of the parameter space allows for sustained nuclear fusion, meaning in his models, 1/4 of the time you scramble the dials, you can still get functioning, long-lived stars.
Wow, a 25% success rate is massively different than 1 in 10 to the 136th.
It is. And Adams also makes a fascinating philosophical point to counter the fine-tuning narrative. He says our universe isn't even maximally life-supporting.
What does that mean? How could a universe possibly be better calibrated for life than the one we are literally alive in?
Well, Adams points out that if the primordial density fluctuations, a parameter called Q, which dictates how clumpy matter was after the Big Bang, were slightly larger, or if the vacuum energy we just spent so much time discussing were even smaller, the universe would actually produce more stars. It would generate more galaxies and mathematically more habitable real estate for life to take root.
So we aren't sitting at the absolute peak of the fine-tuning mountain. The universe could be more efficient. That is a wild thought. The universe is fine-tuned for life, but we might just be living in the cosmic equivalent of a fixer-upper. But here's where I really want to challenge the fine-tuning paradigm, because I read about the Weakless Universe paper from 2006, and this totally threw me for a loop. We are always taught there are 4 fundamental forces: gravity, electromagnetism, strong nuclear force, and the weak nuclear force. And the weak force is specifically responsible for radioactive decay and, crucially, supernovae, right?
Correct. The weak force drives beta decay, and supernovae are absolutely essential in the standard cosmological model because they act as the universe's forges. When a massive star explodes, it distributes heavy elements like iron, carbon, and oxygen into the interstellar medium. Without supernovae, those elements stay locked in dead stellar cores, and you never get rocky planets or biology.
Okay, but physicists Harnick, Cribbs, and Perez proved mathematically that you could entirely remove the weak nuclear force. You could just highlight it, hit delete, erase it from the universe's source code, and still get a habitable cosmos.
They did propose that, yes.
How is that mathematically possible? Wait, you're telling me you can just delete one of the fundamental forces? Doesn't this totally ruin the fine-tuning argument? If we don't even need one of the 4 fundamental forces, maybe life is just incredibly adaptable, like weeds growing through concrete.
It's a brilliant, highly provocative challenge. But creating the weakless universe isn't as simple as just hitting delete. The recipe requires some highly specific, multi-dimensional tweaking to compensate for the missing force. To make it work, Harnick and his colleagues had to heavily adjust the baryon to photon ratio, setting it precisely to 10 to the negative 12.
Why that specific ratio?
Because without the weak force, Big Bang nucleosynthesis, the formation of the first elements in the seconds after the universe's birth, would behave differently. Adjusting the ratio stops the Big Bang from burning all the available hydrogen into helium. They also had to completely remove heavy quarks from the standard model.
What does removing heavy quarks do?
It prevents the formation of certain stable baryons that would wildly disrupt chemistry in a universe without weak decay. But your underlying point stands if you do all of that careful re-engineering. The mathematical result is a universe that still has matter domination, stars that burn stably for billions of years, and crucially alternative mechanisms that still trigger supernovae and distribute heavy elements up to iron, all entirely without the weak force.
See, to me, that feels like a massive blow to the razor's edge theory. It proves there are entirely different recipes for a universe, and it brings up another huge critique of fine-tuning carbon chauvinism. The entire fine-tuning argument always assumes that life must be carbon-based. It assumes we absolutely need the specific long-chain covalent bonds that make up our proteins and DNA, but astrobiologists routinely point to elements like silicon or boron, which have incredibly diverse chemical bonding properties. And we've even seen synthetic biology experiments in labs where scientists create artificial metabolic pathways that don't exist in nature. So if we change the dials, maybe we don't get carbon-based humans, maybe we get silicon-based floating gas creatures in a completely different thermal environment. Life finds a way, right?
That is the standard intuitive counter-argument. However, the physicists deeply aligned with the fine-tuning perspective have a very robust and frankly sobering rebuttal to carbon chauvinism.
Let's hear it.
Their argument is that you are misunderstanding the scale of the destruction. When you change these fundamental parameters like the proton to electron mass ratio or the overarching strength of gravity or the strong force, you aren't just selectively eliminating carbon from the periodic table, you are physically eliminating the possibility of all complex molecular structures, regardless of the element.
Oh, so it's not a matter of saying, carbon doesn't work under these new rules, let's use silicon instead. It's saying the physical concept of chemistry no longer exists.
Exactly. If gravity crushes a star in 1,000 years, it doesn't matter what element you use, there is no time for evolution. If an electron's orbital geometry collapses because the mass ratio changed, it doesn't matter if you are hoping for a silicon-based life form, you literally have no atoms capable of forming stable molecular bonds. You lose macroscopic thermodynamic systems. It's not about losing carbon, it's about losing chemistry entirely. The void remains sterile.
Okay, that is a chilling rebuttal. It really brings back the severity of the numbers. So if we accept Barnes's premise that the fine-tuning is indeed as precise as 1 in 10 to the 136th power, and alternative chemistry is a myth, how did we get so impossibly lucky? If the odds are that astronomically against us, the most popular physical explanation is that we aren't lucky at all. We just bought an infinite number of lottery tickets.
Which brings us directly to the multiverse, and specifically the cosmological mechanism known as eternal inflation.
Let's spend some real time unpacking eternal inflation. Because to the casual listener, the multiverse often sounds like a comic book plot device to bring back dead characters. But it actually has incredibly serious mathematical roots in established cosmology.
It does. It emerges directly from cosmic inflation theory, which is the leading model for the very early universe. Inflation dictates that a tiny fraction of a second after the Big Bang, the universe underwent a brief, superluminal exponential expansion.
Superluminal meaning space itself expanded faster than the speed of light.
Yes, space itself isn't bound by the cosmic speed limit. Only things moving through space are. This immense expansion was driven by quantum fields known as inflaton fields. Now, according to eternal inflation, this expansive state doesn't just stop everywhere all at once.
So the expansion keeps going.
Globally, yes. The inflaton field decays in localized patches, and its energy is dumped into creating regular matter and radiation. This localized decay creates bubble universes through a process called reheating. Our observable universe, everything we can see with our most powerful telescopes, is just the inside of one of these bubbles.
Okay, I'm following.
But here is the critical key. While our bubble has stopped inflating exponentially, the high-energy space between the bubbles continues expanding forever.
Let me try a visual analogy. Think of a boiling pot of water. You have bubbles of steam forming inside the liquid, but imagine the water itself is expanding and growing faster than the bubbles can pop or touch each other. So you have all these distinct bubbles of reality continuously forming in an ever-growing matrix.
That is a phenomenal visualization. The matrix expands eternally, nucleating new bubbles endlessly. And because quantum symmetry breaks differently inside each bubble as it forms, eternal inflation generates an infinite ensemble of universes, each with completely randomized physical constants.
So in bubble A, gravity is too strong and it crushes itself. In bubble B, there's no strong nuclear force, so it's just a hydrogen cloud. In bubble C, the vacuum energy is too high and it rips itself apart instantly. But if you have an infinite number of bubbles, eventually, in bubble infinity plus 1, you get our exact universe.
Yes. Under the multiverse framework, fine-tuning is simply an illusion. It is a textbook case of anthropic survivorship bias. We observe a perfectly calibrated universe not because it was designed for us, but because we could only possibly have evolved in the highly specific bubble where the random throw of the cosmic dice favored complex chemistry. The sterile, dead vacuums exist in uncountable numbers. We just aren't there to observe them.
The math is elegant and it solves the problem perfectly, but is it actually science? Because if these bubbles are causally separated, if the space between them is expanding faster than light, we can never travel to one, we can never see one. How could we ever empirically prove they exist? Is there any actual observational signature we can look for?
That is exactly the question cosmologists wrestled with for years. And they realized there is a theoretical signature we could look for. If eternal inflation is real, it's statistically possible that early on in our universe's history, our bubble expanded in close proximity to another bubble universe, and they physically collided before the exponential expansion of the matrix pushed them apart.
Like two soap bubbles bumping into each other and merging for a split second before flying away?
Exactly. And that titanic collision between two universes would leave a physical imprint on the cosmic microwave background, or CMB.
Let's explain the CMB, because it's vital here. The CMB is the fossil radiation left over from the Big Bang. About 380,000 years after the universe was born, it finally cooled down enough for electrons to attach to protons, which allowed light to travel freely for the first time. The CMB is the afterglow of that moment.
Right.
It's literally a baby picture of the universe, and we map it by measuring incredibly tiny temperature fluctuations in the microwave spectrum across the entire sky.
Perfect summary. Now, if two spherical bubbles collide, their intersection forms a distinct circular boundary. On the CMB temperature map, cosmologists theorize that this collision would manifest as an azimutally symmetric ring or disk. It would have a very specific temperature and polarization profile driven by a phenomenon called the kinetic Sunyaev-Zeldovich effect, or KSZ effect.
The KSZ effect, what exactly is that doing to the light?
The KSZ effect occurs when photons from the cosmic microwave background interact with high-energy, fast-moving electrons, usually in massive galaxy clusters, but in this case, along the turbulent boundary of a bubble collision. The collision boundary would scatter the CMB photons in a highly distinct, recognizable pattern.
So scientists had a target. They wrote algorithms designed specifically to hunt for these cosmic bruises. They pored over the data from the WMAP satellite and the European Space Agency's Planck satellite, which mapped the CMB with unprecedented precision. What do they find when they look for the rings?
They found absolutely nothing.
A complete null result.
An exhaustive, comprehensive null result. The rigorous search of the Planck and WMAP legacy datasets yielded zero statistically significant evidence for bubble collisions. The data constrained the average number of detectable bubble collisions on the full sky to fewer than 1.6, at a 68% confidence level.
Which is essentially zero.
And essentially zero. The Planck data was a triumph for the standard lambda CDM model of cosmology, confirming it with unprecedented accuracy. But it showed our universe is almost perfectly flat and perfectly isotropic, meaning it looks the same in every direction. It entirely lacks the heavy gravitational lensing or the non-Gaussian topological defects you would absolutely expect to see from chaotic bubble interactions in a multiverse.
Okay, so the Planck satellite mapped the sky and basically gave us a blank slate with no bubble collision scars. Is the multiverse theory on life support, are physicists giving up on it?
It is severely constrained observationally, but physicists aren't giving up entirely. They are now turning to future observational probes, specifically targeting the 2025 to 2026 timeframe. They are looking at remote dipole and quadrupole fields, or RDF and RQF.
What are those fields measuring?
By combining precise CMB experiments with massive upcoming galaxy surveys like the data coming from the Vera C. Rubin Observatory's LSST and the CMBS4 project physicists can measure superhorizon scale physics. They are looking at how structures on the absolute largest observable scales interact. They forecast this combined data will increase our constraining power on bubble collision parameters by an order of magnitude. It will be the most rigorous make-or-break test of eternal inflation to date.
But for right now, the multiverse is hiding from our telescopes. There is no proof. So with the multiverse lacking empirical validation, theoretical physicists have started looking to entirely different scientific disciplines to explain the precision of reality. If physics can't explain it, maybe other fields can provide a metaphor. And this is where things get truly wild. We are moving from physics to biology and computer science. Let's start with biology, cosmological natural selection.
This is a deeply fascinating theory originally proposed by theoretical physicist Lise Smolin back in 1992. It's often referred to as the fecund universes hypothesis. Smolin suggested that the universe operates on a biological, evolutionary logic applied at a macroscopic, cosmological scale.
Universe reproduction, a cosmic family tree.
Exactly. Smolin theorized that the singularity at the center of a black hole isn't just a dead end where space-time violently breaks down and ceases to exist. Instead, the singularity acts as a bounce. That extreme gravitational bounce generates a new, causally disconnected child universe on the other side of the event horizon.
So a black hole in our universe is literally the Big Bang for a brand new child universe.
Right, and crucially, the child universe inherits the physical parameters of its parent, things like the fine structure constant, the masses of quarks, the strengths of gravity. But because of the extreme, chaotic quantum gravitational dynamics at the bounce point, there are slight stochastic mutations. The child's dials are turned just slightly differently than the parents.
I see exactly where this is going. Over countless generations of universes, the universes that possess the optimal parameters for creating stars which eventually run out of fuel and collapse into black holes will produce the most offspring.
Darwinian evolution on a cosmic scale. The multiverse landscape becomes completely dominated by universes mathematically fine-tuned for maximal black hole fecundity.
But wait, what does a universe optimizing itself to make black holes have to do with us? What does that have to do with life?
This is the brilliant synthesis of Smolin's theory. The fundamental physical parameters required to build black holes specifically, the parameters that allow for complex atomic structures, molecular cooling, and long-lived stellar fusion, are the exact same parameters required to support complex chemistry.
Oh, wow.
So biological habitability emerges naturally as a highly probable, incidental byproduct of cosmic evolution. The universe doesn't care about us. We're just along for the ride in a cosmos optimized for black hole reproduction.
That is incredibly poetic. It gives the universe a drive, a purpose. But the absolute best part about Smolin's theory is that unlike the standard multiverse, it actually makes a rigid, falsifiable prediction. He put his money where his mouth is.
He did, which is a rare and highly respected move in theoretical physics. Smolin predicted that if our universe is truly optimally tuned for black hole production, there can be no physical mechanism that would allow a neutron star to grow indefinitely without collapsing into a black hole.
Right.
Based on complex calculations regarding how can condensates soften the equation of state in dense matter, he drew a hard mathematical line. No stable neutron star could exist with a mass greater than approximately 1.6 to 2.0 solar masses.
Let me translate that. Anything heavier than 2 times the mass of our sun should immediately crush itself into a black hole. Did that limit hold up to observation?
Unfortunately for cosmological natural selection, no. Recent astrophysical discoveries have dealt a severe, possibly fatal blow to this original formulation. In 2019, astronomers using radio telescopes found a rapidly spinning neutron star, PSR J0740 plus 6620, with a firmly measured mass of 2.08 solar masses.
It broke the absolute upper limit.
And the observations only got worse for the theory. Subsequent discoveries found pulsars like PSR J09520607 reaching up to a staggering 2.35 solar masses. These physical observations technically falsify Smolens's rigid threshold, because if our universe was truly perfectly optimized by evolution to maximize black hole production, parameters like the mass of the strange quark should have evolved to trigger gravitational collapse at a much lower mass threshold.
We should be making black holes easier if that was the universe's prime evolutionary directive. And I know string theorist Leonard Susskind also heavily critiqued this biological idea, right?
Yes, Susskind pointed out a major flaw in the logic. He noted that the laws of physics allow for theoretically lumpier universes. Universes where matter is far less evenly distributed. These lumpy universes would have vastly higher black hole production rates than ours. So if natural selection are true, and black hole reproduction was the only metric of success, we wouldn't be in this relatively smooth, flat universe. We'd be in a chaotic, lumpy one filled with singularities.
Despite those massive hurdles, the core logic of universe evolution is still surviving in physics departments. We've got theorists updating the model using Price's equation from evolutionary biology to account for these heavy neutron stars. And there are even new cosmological learning models from 2021, like the Autodidactic Universe paper, which suggests the universe operates less like a biological organism and more like a machine learning system, updating its own laws based on accumulated complexity. But if the universe isn't a biological organism evolving, what if it's a computer? Enter the simulation hypothesis.
Between 2024 and 2026, the simulation hypothesis genuinely began transitioning from philosophical musing, the kind of stuff you talk about in a dorm room at 2 a.m., into rigorous physical science. This transition was heavily propelled by rapid advancements in artificial intelligence and quantum computing.
Right, because under the simulation framework, the fine-tuning problem is completely trivialized. The reason the strong force is exactly 0.007 is simply because the higher dimensional programmer typed 0.007 into the physics engine. But how do we actually test that? It sounds unprovable.
Santa Fe Institute professor David Wolpert established a mathematically precise framework for nested simulations. He applied the physical Church-Turing thesis to cosmological scales. The Church-Turing thesis essentially asserts that any observable physical process can be reproduced by a computer program.
Okay, let's unpack Wolpert's math. He used something called Kleen's second recursion theorem, right?
Yes. Wolpert demonstrated mathematically that a universe capable of simulating another universe could technically be reproduced inside its own simulation. He mapped the absolute logical boundaries of computational reality. And proponents of this theory look at our universe and argue that it already exhibits clear physical signatures of underlying computation.
This is the part of the theory that genuinely fascinates me. Let's look at the code. What are the physical signatures that suggest we are in a simulation?
The first major signature is the Planck scale. Reality seems to be embedded with a baseline resolution. There are impassable minimum limits of length and time. The Planck length is about 10 to the negative 35th meters. You cannot physically divide space any smaller than that. It acts as a finite level of granularity.
The voxel grid? The literal pixels of reality. Space isn't smooth, it's made of tiny, discrete blocks.
Exactly. The second signature is quantum indeterminacy. Phenomena like wave function collapse and the observer effect mimic real-time rendering algorithms used in modern video games.
Oh, this is so cool.
Right. To save processing power, a game engine only highly resolves an environment, loading the high-resolution textures and physics when a player actually looks at it. Quantum systems exhibit strikingly similar behavior. A particle exists in a blur of probability prior to measurement.
Oh man, the universe is literally saving RAM by not rendering the atom's exact position until I look at it. And the third signature is the holographic principle, which we mentioned earlier with Shannon entropy. The maximum entropy of a volume of space is proportional to its surface area, not its volume, which maps perfectly to data storage limits. It's like the universe has a strict gigabyte cap on every sector of space.
I love this theory. I really do. It makes so much intuitive sense. But I have to pivot hard here, because as much as I want to believe we are living in the Matrix, physicist Sabine Hossenfelder delivered a completely devastating critique of this entire field. She basically asked, is the simulation hypothesis just the modern equivalent of saying the gods did it? Hossenfelder argues exactly that. She states it's intellectually lazy. Pointing to the sky and saying, the programmer did it, serves as modern mythology. It offers absolutely no genuine explanatory power for how the universe functions. But her critique goes much deeper than philosophy. She points out severe, fatal physical contradictions in the simulation logic.
Like what? What breaks the simulation model?
Our universe features continuous symmetries and Lorentz invariance. Lorentz invariance dictates that the laws of physics are exactly the same for all observers, regardless of their velocity or their orientation in space. But a simulation built on a discrete, pixelated lattice of bits fundamentally violates continuous symmetry.
Because on a grid, moving diagonally across the pixels is mathematically different than moving strictly up or down. A grid has a preferred direction.
Exactly. If reality were truly a pixelated grid, we should be able to detect slight, measurable violations of these symmetries when we observe extremely high-energy particles interacting. But exhaustive astronomical searches for these cosmic discretization violations have yielded completely null results. Space appears perfectly, continuously smooth at all observable energy levels, not pixelated.
And what about quantum computers? Simulation proponents always say, well, it's not a classical computer on a rigid grid, it's a quantum computer. Can't quantum computers simulate a smooth space?
That's the other massive issue she points out. A classical computer cannot simulate quantum effects like entanglement without an exponential, impossible slowdown. And while a quantum computer using qubits could theoretically bypass that specific slowdown, current theoretical physics has completely failed to reconstruct general relativity and the standard model purely from qubit interactions.
Ah, I see.
You can't just wave a wand and say qubits do it. Ostenfelder concludes that until simulation proponents can solve the actual, rigorous mathematical mapping of quantum gravity onto a computational lattice, the hypothesis remains fundamentally unfalsifiable pseudoscience.
Ouch. So the simulation hypothesis is on incredibly thin ice physically. But whether we live in a multiverse, an evolving black hole family tree, or a simulation, any cosmological theory that relies on infinite time or infinite space eventually runs headfirst into what might be the most terrifying concept in all of cosmology, the epistemological nightmare, the Boltzmann brain paradox.
This concept was initially architected in the late 19th century by physicist Ludwig Boltzmann to challenge the idea of an eternal infinite universe. But it has evolved in modern times into a genuine thermodynamic crisis for theories like eternal inflation.
If you're listening to this right now, I want you to really think about what this paradox means for your own consciousness in this exact moment. Let's set the stage. What is the ultimate, final fate of our universe?
Heat death. The de Sitter vacuum. Trillions upon trillions of years from now, all the stars will burn through their fuel and die. The galaxies will drift apart. The black holes will slowly evaporate through Hawking radiation. And the universe will reach a state of complete thermal equilibrium. A dark, cold, featureless void where nothing happens.
But it's not totally dead because of quantum mechanics, right? The vacuum is still boiling.
Right. Even in a completely dead universe, random quantum and thermal fluctuations will inevitably occur. Particles will momentarily pop into and out of existence from the vacuum energy. Over unimaginable timescales, we're talking time frames like 10 to the power of 10 to the power of 50 years, these random microscopic fluctuations will eventually, simply by chance, assemble every possible combination of matter.
And here's the horrifying, mathematically inevitable consequence of infinity. If you wait long enough, random chance will perfectly assemble a fully functioning, biologically accurate human brain out of the void.
Complete with false memories of an entire life, an evolutionary past, and the sensory illusion of perceiving a finely tuned cosmos. You will exist for a fraction of a second, have a single conscious thought, and then dissolve immediately back into the darkness.
The Boltzmann brain. And the core of the paradox is this. If time is infinite and these momentary brains are constantly fluctuating into existence over eternity, they will eventually vastly outnumber real biological observers who evolved the hard way over billions of years.
Exponentially outnumber. If kernel inflation is true and the universe lasts forever, statistically, you are overwhelmingly likely to be a momentary hallucination right now. You are not a biological entity listening to Audio Notebook. You are a Boltzmann brain, floating alone in a dead void, hallucinating this entire experience.
That induces genuine existential dread. Physicists call it cognitive instability, because if our minds are just random fluctuations, our memories are fake, our science is fake, our derivations of the laws of physics are completely untrustworthy. It undermines the scientific method itself because you can't trust your own brain's observation of reality. Please tell me how physics gets us out of this nightmare.
Thankfully, between 2024 and 2026, significant theoretical breakthroughs emerged that attempted to resolve this thermodynamic nightmare. The first is the many worlds fix, proposed by physicists Sean Carroll and Jason Pollock.
Okay, what's their angle on fixing this?
They argue the paradox relies on a fundamental misunderstanding of quantum mechanics. In an infinite dimensional Hilbert space governed by many worlds quantum mechanics, the de Sitter vacuum, that cold and dead end state of the universe, is a truly stationary, time-independent state.
What does time-independent mean for our hallucinating brains?
It means that the act of observation requires out-of-equilibrium dynamical processes. Things have to actually happen and change over time. But in a truly stationary vacuum, thermal fluctuations don't dynamically occur in a time sequence. Therefore, Boltzmann brains do not actually fluctuate into physical, observable existence. They are mathematical possibilities that never actualize.
Okay, that helps the dread a bit. But there was another even more profound resolution in 2025. The entropy conjecture by David Wolpert, Carlo Rovelli, and Jordan Scharnhorst. They completely reframed the paradox using stochastic process theory. I'm going to need you to thoroughly break down what a time-symmetric Markov process is. Let's use a tangible analogy, like flipping a coin, to explain this memoryless probability, because I need intellectual relief from this paradox.
I can absolutely do that. They formalize the evolution of the universe's entropy as a time-symmetric, time-translation invariant Markov process. A Markov process is a sequence of possible events in which the probability of each event depends only on the state attained in the previous event.
So if I flip a coin 10 times and it lands on heads 10 times, the probability of the 11th flip is still exactly 50-50. The coin has no memory of the past 10 flips.
Exactly. The system is memoryless. Now, when physicists usually calculate the probability of a Boltzmann brain, they condition the entropy on a low entropy Big Bang. This is called the past hypothesis. They look at the universe and say, given that the universe started highly ordered and is moving toward chaos, how likely is a fluctuation?
Right.
Wolpert, Rovelli, and Scharnhorst proved mathematically that the fundamental equations of physics inherently lack a mandated conditioning time.
Meaning what?
The assumption that we must condition our probabilities on a low entropy Big Bang in the distant past, rather than conditioning them on our current present observations, is an arbitrary philosophical choice. It's not a physical law. It's a bias humans bring to the math because we experience time moving forward. By formalizing the math without that bias, they demonstrated that predicting a universe dominated by Boltzmann brains relies on subtle forms of circular reasoning regarding time asymmetry and memory reliability.
So the paradox completely dissolves. It's a mathematical artifact based on a biased, human way of looking at time. That is a massive relief. I am real, you are real. The coin doesn't remember the Big Bang.
As far as rigorous physics is concerned, yes, we are not hallucinations.
Good, because all these paradoxes, the multiverse, the simulation, the Boltzmann brains, they all exist because of a fundamental schism in physics. To truly know if the fine-tuning is an accident, an anthropic necessity, or a mathematical inevitability, we need a theory of everything. We need quantum gravity.
The schism you mentioned is the deep conflict between general relativity, which excellently describes the macro-universe, gravity, black holes, and the curvature of space-time and quantum field theory, which accurately describe the micro-universe subatomic interactions and the other three forces. They mathematically refuse to work together. When you try to use both sets of equations to describe the center of a black hole, you get infinities. The math breaks. Three primary candidates currently dominate the theoretical frontier to unite them.
Let's start with the most famous one, the one that's had a stranglehold on theoretical physics for decades: string theory.
String theory posits that fundamental particles aren't zero-dimensional dots, but rather one-dimensional vibrating strings of energy operating across 10 or 11 dimensions. The exact geometric shape of these extra curled-up dimensions, known as Calabi-Yau manifolds, dictates how the strings vibrate. That specific vibration determines the mass and charge of particles in our observable 3D world.
And how does string theory handle the fine-tuning problem? Does it explain why the dials are set the way they are?
It fully embraces the multiverse. String theory famously produces a landscape of up to 10 to the 500th power mathematically valid vacuum solutions. Each possible solution represents a universe with different physical laws, different particle masses, and different cosmological constants.
10 to the 500. So it essentially throws its hands up and says, yes, there are an unfathomable number of configurations, and we are just in the one that allows life.
Exactly. But severe critics argue this sheer volume of possibilities destroys any real predictive power. If your theory can predict absolutely any conceivable universe, it technically predicts nothing at all. It makes string theory extremely difficult, if not impossible, to falsify.
Okay, so what about candidate number 2, loop quantum gravity, or LQG? How does that differ?
LQG takes a completely different approach. It attempts to quantize space itself without requiring any hidden extra dimensions. It suggests space-time is not a smooth continuum, but a discrete web of finite interlocking loops woven into spin networks. Time is simply the dynamic rearrangement of these networks, called a spin foam.
So space is quantized, it's chunky. But LQG recently took a massive hit, right? The LASO blow. Wait, what exactly is LASO measuring? Are they catching photons from across the universe?
They are. LASO stands for the Large High-Altitude Air Shower Observatory. They are detecting the cascading showers of particles created when ultra-high energy gamma rays from deep space hit Earth's atmosphere. Now, a discretized, chunky spacetime inherently predicts Lorentz invariance violations, or ULIV. This means that the speed of light should vary slightly depending on a photon's energy as it navigates this bumpy quantum geometry over billions of light years.
Higher energy photons would traverse the quantum bumps differently than lower energy ones, so they should arrive at Earth at slightly different times.
Exactly. But recent data from LASO placed extremely stringent constraints on these violations. They measured these high-energy photons traveling vast cosmic distances and found they all arrived exactly as expected, completely obeying the standard speed of light. This pushed the energy scale of any such violation to 10 times the Planck energy. This empirical data dealt a devastating blow to linear-order LQG models.
The space simply isn't bumpy enough for LQG to work. So string theory predicts too much, LQG predicts bumps that aren't there. This brings us to the underdog hero of theoretical physics, causal dynamical triangulation, or CDT. This is spearheaded by physicist Renate Lowell.
Yes, CDT takes a non-perturbative, background-independent approach. Instead of assuming a background space exists and putting things in it, it builds space-time from scratch out of tiny triangular Minkowskian building blocks known as simplices.
So you throw these tiny geometric triangles into a computational path integral, and what happens?
They self-organize. According to the rules of quantum mechanics and strict causality, meaning cause must always precede effect, these microscopic blocks stitch themselves together in the computer simulation, and the incredible breakthrough is that a smooth, four-dimensional de Sitter universe closely resembling our own macroscopic universe emerges dynamically from the simulations.
Without extreme fine-tuning, you don't have to put the constants in by hand.
Exactly. The 4D structure arises robustly from the geometry itself. Furthermore, CDT provides a falsifiable quantum signature. It predicts that the dimensionality of the universe is scale-dependent.
Okay, this is where I need you to clarify. How exactly does scale-dependent dimensionality work? It operates in 4D at our macro scale, but collapses to a 2D fractal geometry at the Planck scale. How does 2D at the smallest scale create 3D plus time for us?
Think of a tightly wound garden hose.
Yeah.
From 100 feet away, it looks like a one-dimensional line. But when you walk up to it, you see it has a two-dimensional surface and a three-dimensional volume inside. CDT suggests the universe is somewhat the reverse.
Oh, that makes sense.
At our massive macroscopic scale, we perceive 3 dimensions of space and 1 of time. But as you zoom in closer and closer to the Planck scale, the causal links between those microscopic triangular simplices become highly restricted. The paths available for interaction collapse. The geometry mathematically reduces to a two-dimensional fractal web.
That is wild. And it is so much more scientifically satisfying than string theory's infinite landscape. String theory says anything is possible, we're just lucky. CDT says, no, the fundamental geometry of causality naturally builds a universe like ours. It gives us a physical, geometrical reason.
It does. It offers a genuine glimmer of hope for a purely naturalistic, non-anthropic theory of everything that derives the constants from first principles.
But what if CDT fails to pan out? What if theoretical physics remains completely unable to derive these exact constants from first principles? If the math never solves the fine-tuning, we are left with the ultimate philosophical fallback, the anthropic principle.
Coined by Brandon Carter in 1974, the anthropic principle relies entirely on observation selection effects. We have an inherent, inescapable bias because we can only ever observe a universe capable of generating observers.
Let's break down the two flavors of this. The weak anthropic principle, or WAP.
WAPA asserts that our location in space and time is necessarily privileged out of sheer necessity. It's just survivorship bias. Just as we aren't surprised to find ourselves evolving on a wet, temperate planet orbiting a stable star, rather than floating in the radioactive void of deep space, we shouldn't be surprised to find ourselves in a rare, life-permitting bubble universe.
We're here because we literally couldn't be anywhere else. But then there is the strong anthropic principle, SAP.
The strong anthropic principle takes a much more aggressive, controversial stance. It asserts that the universe and its fundamental parameters must be structured to admit the creation of observers at some stage within it. This borders heavily on teleological purpose, suggesting that consciousness is the universe's ultimate intended function.
I genuinely grapple with this, because critics of anthropic reasoning call it a massive philosophical sleight of hand. And I agree, it feels like, imagine you are blindfolded, put against a brick wall, and subjected to a firing squad of 1,000 expert marksmen. The commander yells fire, you hear the deafening roar of 1,000 rifles, but you are completely unharmed. When someone takes off your blindfold and asks you, how did you survive 1,000 expert marksmen? You just shrug and say, well, if I didn't survive, I wouldn't be here to answer the question.
It's a textbook logical tautology.
Yes, it's completely true that you have to be alive to observe your own survival, but that observation absolutely does not explain why 1,000 expert marksmen all miraculously miss, saying, we are here, therefore the constants are right, stalls deeper physics. Accepting the anthropic principle is basically surrendering. It is abandoning the scientific pursuit of deriving reality's properties from unbroken, fundamental laws.
It is the ultimate surrender of the physicist. Which brings us to a synthesis of everything we've explored today. We are standing at a profound epistemological crossroads in human understanding.
Let's summarize the board. Where do we stand?
Cosmological natural selection. The idea of a biological, evolving universe has been deeply wounded by the discovery of heavy neutron stars that break its core predictions. The multiverse remains hidden by the strict empirical constraints of the Planck satellite data. The simulation hypothesis is marred by its failure to respect continuous symmetry and Lorentz invariance.
And we are left hoping that theories like causal dynamical triangulation can mathematically prove that space-time naturally weaves itself into a stable four-dimensional reality without needing a numerical miracle.
Exactly. From the catastrophic 10 to the 120th power error of the cosmological constant to the razor-thin 0.007 efficiency of the strong nuclear force, the architecture of reality undeniably appears optimized for complexity. Whether these incredibly delicate parameters are the result of mathematical inevitability, an infinite multiverse, or something entirely beyond our current scientific grasp, it continues to push the absolute boundaries of human knowledge.
Thank you for joining us on this intensely detailed edition of Audio Notebook. We have gone from the decay of a single neutron to the ultimate heat death of the cosmos. But I want to leave you with one final provocative thought to mull over, something that builds on everything we've discussed today. We've talked extensively about how the universe seems perfectly calibrated to produce observers, and we talked about how quantum systems remain unresolved probabilities until an observer actually looks at them. If consciousness is indeed the only mechanism by which the universe can observe itself, perhaps the observer effect in quantum mechanics isn't just a quirky byproduct of simulation rendering. Perhaps it is the very structural foundation that solidifies the cosmological constants into place. Until general relativity and quantum mechanics are finally reconciled, the reason why the cosmos chose sapience over a silent, featureless void remains yours to ponder.